Well, welcome back, guys, and as ever, I do hope you and your family are keeping well. It's such a shame you can't be with me here in the laboratory doing this physics. But what we're going to do now is do our fourth lesson on capacitors. We're going to look at capacitors discharging. In other words, we've put some energy onto them. How can we get that energy back off them and get them to do some work? So we're going to look later on at how capacitors charge up. But what we know already is that if we connect them to a power supply with no resistors in the circuit, they'll charge up pretty quickly, and then the voltage on them will stay constant at the same voltage as that of the supply, and that the current in the circuit will drop to zero. So the capacitor's charged to the same voltage as the battery. Okay, but what I wanted to look at now was what happens when we discharge the capacitor. So we connect the capacitor to an external circuit, removing the battery. Okay, the energy in the capacitor is then going to flow off it. Okay, so as you would probably guess, there's going to be a current in the circuit, I. But as there's less and less charge on the capacitor, that current will go down and down and down. The voltage across the capacitor will drop off as well as it loses its charge. Okay, it's going to lose its charge. I've just mentioned that. So Q equals CV. All of these all drop off to a point where the capacitor loses all of its charge. The charge neutralizes, so there'll be no current, no voltage, and no charge separation on the capacitor. Now, that's not enough for A-level. What we need to know is that these drop away exponentially, and I'm going to explain why that is later on. So they're going to fall away exponentially. And if you remember, exponentials, you've probably come across them in radioactivity with half-life and things like that, are kind of governed by specific numbers in physics, and in this case the exponential decay is governed by E, and this is the logarithm, the natural logarithm, and you might remember that the number E is approximately equal to 2.72. It goes on further than that, but it's a sort of decimal that goes on and on, but we can abbreviate it to about 2.7 or 2.72. It's a constant and it doesn't have units. But this number is going to crop up again and again when we do circuits that involve discharging capacitors. So now let's look at a circuit that we're going to use to show how a capacitor discharges, and I think you'll recognise it. And with these things, it's always important, I think, that I draw them in front of you. So here's our circuit, and it's going to be a circuit that will double up as a circuit that can charge a capacitor, and it can also discharge it. So if you remember, we need a power supply. So I'm going to draw the battery that charges the capacitor here. Have the ability to turn it on and off. So that's kind of my bit that provides the energy for charging. And then I'm going to draw the circuit that we're interested in, which is a capacitor. So here's the capacitor. And you get very used to these kind of drawings. And it's a capacitor, well, it's going to look as if it's in parallel. But if you follow the purple circuit that I'm drawing around, you'll notice really what this is a capacitor sort of, well, it is in parallel, but imagine it as a series circuit really is the best way to think about it. And finally, we need some measuring tools. So let's put across here. I'll do it across there and there, though, across the resistor as well. It's exactly the same as across the capacitor. A voltmeter. Okay. So we've got some values here that we can look at. We've got C, the capacitance, R, the resistance of the external circuit, and V, the value on the voltmeter. Now, remember that when we flick this switch, a number of things happen. Charge will flow onto the capacitor and charge it up. When the capacitor is, shall we say, fully charged, okay, when the charge is fully separated to produce the same voltage here as across the battery, there will be no more current in this branch. But at all times when turned on, there will also be a current through the resistor, and that is governed by V equals IR. So simple sort of Ohm's law type physics there. So if you think about it, there's something complex that happens when you switch on. The capacitor charges and then stops, and the current stops here. But the current here just keeps going for as long as that switch is connected. So that's the sort of charging bit. And once the capacitor has settled down and gets the same voltage as the power supply, then the power supply voltage, we'll call that V0, okay, will be the same as the voltage all the way across this circuit, but especially across the charged, shall we say fully charged capacitor. Okay. Now, here's the clever bit. Okay. Let's now switch this on. So I'm going to put a little note here to say when switched on, now, there's no resistance really. Consider that to have negligible internal resistance. There's no resistance in the capacitor circuit. So current rushes in, charges the capacitor, and in a very short amount of time, we can later on calculate that actually, the capacitor will be charged. Okay, so when we switch it on, this is the charging cycle, we need to wait a few moments. So after a few moments, isn't that a technical term? Okay, I mean, it's a second. It's a very short space of time. It's much less than a second, actually. What can we say? Okay, well, using V equals IR, so we've got an R here, and we've got a V, okay? We can work out the current in the resistor. So I is V over R, so we can say I, the current in the resistor, yeah, will be equal to the voltage across it, which is V0, divided by its resistance. Okay, that's something we can say at all times that switch is switched on. Okay, there'll be a current in this resistor. But if we leave the circuit for a few moments, that will stay the same, but the capacitor will be completely charged up. So we can say that the current in through the capacitor branch after a few moments will be 0 because the capacitor is fully charged. We can also say something else, that if the capacitor is charged up, the voltage on the capacitor will be the EMF of the power supply, the voltage on the power supply, okay, or at least very, very close to it. And we can say that Q, the charge stored on the capacitor, will be equal to CV. And because the V is the power supply's voltage, we can say the charge stored on the capacitor is CV0. Now, that's of course not what I wanted to do with you today. What I wanted to do was say, right, we've reached the steady state of the capacitor charged up, now disconnect the battery. So in my classroom, it's kind of connect the circuit and then unplug, maybe just unplug that lead. Okay, now what happens to the voltage across the circuit, which is the same as across the resistor and the capacitor? What happens to the current in the circuit? Okay, and what happens to the charge on the capacitor? Because as soon as we switch off, that capacitor will now discharge through this resistor because it's got a resistor connected, in this case we can say in parallel, connected across it. And it's that I want to look at in detail. So now let's get to what I wanted to do today. So what happens when we switch off the power supply? So here's our circuit. We've removed the power supply. Remember, the capacitor at that time, t equals 0, is fully charged, and now it's ready to discharge through this resistor. Okay, so here's our capacitor, C, and here's our resistor, R. Okay, and I'd like you to think that maybe the value of R will affect how it discharges, maybe how much charge we can get on the capacitor. The size of the capacitor affects how it discharges, and you'd be right, and we're going to look at that a bit later on. So the way I look at this is I say, well, this is quite interesting. If you look at this, the capacitor has now sort of become the battery. The capacitor's the bit with the energy stored on it, and it's now going to have charge. The electrons will come off the negative plate through the resistor and onto the positive plate to discharge, but the current, of course, goes the other way around. And the capacitor will discharge, because here what we notice is the capacitor becomes the battery, as it were, becomes the power supply. And obviously, if it's the power supply and it's got a fixed amount of energy in it, then it will discharge. Okay, so it discharges. Good word, isn't it? Okay, to discharge, to kind of give out. It's sort of similar to the words we use in English normally as well. So let's have a look at a specific situation. Okay, let's have a look at the very moment we disconnect the battery. In other words, switch off the charging battery. So let's have a look just as the battery is switched off, disconnects. Okay, now this is a situation that you really have to kind of see and understand well. So what you're left with there, as I said before, is a charged capacitor connected to a resistor in series, in parallel, doesn't really matter with this circuit, and the capacitor is now going to provide the energy. It's going to be the power supply for a short period of time. Okay, well, we know that V equals IR. Okay, so V equals IR. And right at the very start, okay, the V on the capacitor was the battery's voltage. So that will be equal to I in the resistor of the resistor, if that makes sense. Okay, so this gives us the voltage across the capacitor and the current through the resistor. But isn't that interesting? Because this current is also going through the resistor, but it's also kind of going through the capacitor. So this will also be the current in the sort of capacitor branch. Now, you've got to be really careful here. This is the initial current. When the capacitor is fully charged, it's got the voltage of the battery on it, and so it will drive that current. Okay. Now, what that enables you to do is two things. It enables you to answer the question, what is the initial current in the circuit? Or more importantly, what is the initial current through the resistor? Okay. But the problem is, as time ticks away, the capacitor will discharge, lose charge, okay, and therefore will have a lower voltage on it. So as time continues, it's worth pointing out that the voltage on the capacitor will go down as it discharges. So if you think about it, therefore the current in this circuit will go down because the resistance stays the same in the resistor. And finally, okay, it will go to zero as all the charge has moved through the resistor and has neutralized the other plate on the capacitor. And then, of course, the voltage on the capacitor, the voltage across the resistor, which will always be the same value, is zero, and the current in the circuit will be zero. So, do you remember me hinting at the fact that it starts fully charged and then it discharges and discharges and discharges? And it's that shape of graph that's exponential, and it's that we've got to look at next. So let's see if we can explain this graphically. Okay. Now I hinted to you that this is a form of exponential decay. And something you need to know about exponential decay, if you don't know it already, is it has a particular mathematical property which makes it easy to deal with. It has the property of a constant ratio. Now let me just quickly explain what I mean by that. Okay, if you choose an interval of time, okay, so you just say, okay, I'll go for 10 seconds, and you work out by what fraction the voltage has dropped by. If you go to the next 10 seconds, it will have dropped by the same fraction, and you go to the next 10 seconds and it will have dropped by the same fraction again. What I mean by that is, okay, that if, say, in the first 10 seconds it drops by a quarter, then in the next 10 seconds, whatever you've got now will quarter, and in the next 10 seconds, whatever you've got left will quarter and quarter and quarter and quarter. Now, can you see that you're quartering a large amount at the start, and then you're quartering less and less and less and less? Half-life in radioactivity, we just choose, we don't have to, but we just choose to see how long it takes for half the atoms to decay. And that amount of time, if you wait for that amount of time again, it halves again. So let's have a look at this in a more graphical way. So I'm going to draw 3 graphs to explain how does the current change with time, how does the voltage change with time, and how does the charge on a capacitor change with time. So remember, this is what happens when capacitors are discharging, disconnected from the power supply. So I think I'll draw my axes first, and then I'll start to label them. Okay. And I kind of, whilst I'm drawing, I kind of always say to my students, the reason I haven't prepared this in advance is not because I'm lazy. I find it's easier if you understand things if I kind of build it up in front of you as I go along. Okay, so here goes for the first graph. Let's make this graph the current graph. The current in the circuit once you disconnect the power supply. Okay, so there's going to be a current at the start, and we'll call that current I0. Okay, if you remember, we can calculate that because we did it up here. Okay, you can see that the current in the circuit will be V0 divided by the resistance. It might be a bit small on the screen, this, but V0 divided by the resistance. That is this value here. Okay, so you might get asked for that in an exam. What's the initial current? The voltage across the capacitor at the start, which is the same as the battery, divided by the resistance it discharges through. And then the current will drop away with time exponentially. So I'll come over here to draw that. There we go. And we'll get this kind of shape. Now, if you're confident with that, then we can immediately say, okay, well, how does the voltage across the capacitor change with time? Now, you notice I'm not putting any numbers on yet, bar, we can talk about the very starting value, because the very starting value will be V0, because that was the voltage the capacitor was connected to on the battery at the start, and it will hold that voltage on it until you disconnect the battery, and then, of course, we get a flow of charge in the circuit through the resistor. So, here we go. Now, I don't want to say that these graphs are identical because you might get into the feeling that I should have just drawn that on that axis, but these are measuring different things, different quantities in physics. So, finally, how does the charge on the capacitor change with respect to time? Okay. Well, we know that the starting charge on the capacitor, Q0, so that's the charge at time t equals 0, is given by Q equals CV. Okay, so this value here will be Q0 is equal to C multiplied by V0. Okay, the voltage on the battery. And then we disconnect, and of course the charge flows off the capacitor, and I think you've guessed it, an exponential decay. Okay. Now, I might get myself in a bit of trouble here, but I'll try and explain it quickly. Take this value, take an equal amount of time, and it will have dropped. In this case, it looks as if it's halved, but okay. Take another equal amount of time, it looks as if it's halved again, another equal, okay. That would be the proof that it's exponential. But with capacitors, we don't find the half-life very useful. Okay, that's good for atoms, it's not really very good for capacitors. So we're going to look at a different way of analysing these graphs. But my final thing to say is, we need some numbers, and at A level they might say to you, after 3.67 seconds, what's the voltage on the capacitor? And if you haven't got the graph, you can't just go like that. You're going to have to calculate it mathematically, knowing the equation of this line. So what we've got to do next is look at what the equations for these lines actually are. Okay, now for a bit of maths, and we can't avoid this, a way of getting the equation of the line, and then that will allow us to do calculations of values of current, voltage and charge on capacitors at any time after T0. So it's an exponential decay. So we'll start off with how the current behaves, and then I think if you get that, the other two, the voltage and charge, are pretty obvious. So what's the current now? Okay. So you've disconnected the battery, you've set your stopwatch, tick, 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 you've waited a few moments, maybe longer than moments, you've waited a few seconds, and you stop your stopwatch and you said, right, what's the current flowing now? Well, you know it's going to be less because the capacitor's discharging. Well, it's going to be not as big as the starting current. So that statement is incorrect. It's going to be lower than the starting current. And all we need to do, and I'm not a brilliant maths teacher, as you're probably noticing, what we need to do is we need to reduce this number. So we need to multiply it by a number that will make it smaller, a number less than 1. Okay, not a negative number, but a number that will make it less than, that number here will be less than 1, so this number is reduced. Okay, so it's an exponential decay, okay, and E is that number 2.72, okay, raised to the power of T, how long you counted for, divided by the capacitance multiplied by the resistance. Okay, there's a catch, I'm still not correct yet, bear with me. Okay, but this is a positive number. So hang on, we want the the current to drop away. So this power of E is negative. Okay. Now, if your maths is good, you're probably well ahead of me now. If you're struggling with this bit of maths, stop, pause the video, okay, and ask yourself a number of things. Number one, what do all these letters stand for? I'll tell you again. The current now, what the current was at the start, E, which is just 2.72, okay, raised to the power of minus how long you counted for, divided by what the capacitor value is and what the resistor value is multiplied together. Okay. Now, you need to be able to use your calculator to work stuff out here. You need to find the button that is E to the power X, okay, if you had to work something out here. So those are all skills to learn. And you would work out the T over CR. Make sure you make it a negative value, okay, because the time won't be negative, the capacitance and resistance won't be negative. It is minus T over CR. Okay, CR is very interesting. CR is a really interesting number, but we'll come back to that. Okay, and then you raise E to the power of that, and you'll get a number like 0.2. Okay, so that means after that amount of time, the current has dropped to 0.2 times what it was, a fifth of what it was. Okay, so what we'll do quickly now is we'll look at the other two equations for voltage and charge as time ticks away when a capacitor discharges. So once you feel competent with that one, okay, the voltage on any capacitor as it discharges will be the voltage that was on it at the start, that of the power supply, reduced by the same factor. How long you wait divided by the capacitance multiplied by the resistance. And it's a negative power because it reduces V0. Well, you can almost guess what the charge on the capacitor will be after waiting a certain amount of time. I suppose you could put Q sub little t there. Yeah, Q at time t. But no one seems to bother. Okay, Q0 e to the minus t upon CR. When I did this at school, I learnt this as Q equals Q0 e to the minus t upon RC. Well, who cares if it's CR or RC? But I still occasionally say RC instead of CR, but it's the same thing. Okay. Now, there's just one other thing I'd like to note. If you have to work out values of T or CR, this is a little bit fiddly. So you've got to get rid of the E, so you take logs of both sides. I'll do the voltage one, yeah. You take a log of this side, so the natural log of the voltage, okay, will be the natural log of the starting voltage. And then, again, my appallingly poor maths teaching, taking the natural log, okay, basically gets rid of the E. I can't explain to you why, but for those of you mathsy, you don't need me to. And for those of you who struggle with the maths, okay, basically just get rid of the E and this all drops down. It's a very lazy way of explaining it, but minus T upon CR. Let's make that look like a C. Okay, so what we've done is taken logs of both sides of any of the equations, okay, and that allows us then to bite into this one because we can work out what easily on the calculator that quantity, this one, and so we can start to work out maybe what the time it was left for was, or what the capacitance is, or what the resistance is. You obviously have to have only one unknown there. Good. So we've now got the equations of those exponential graphs that I drew a little bit earlier on. Okay, so let's now see if we can put this to use and see if we can do an example. And the one I'm going to choose to do is, what is the voltage on the capacitor after a certain amount of time discharging? Well, there's an easy answer to that. If you leave it for millions and millions and millions of seconds, 0. But I'm not going to leave it for that long. Okay, so if you remember, this is what the circuit looked like. So we had, because it's good to, draw the circuit again so you remember these things. So here was our charging device, our charging battery, okay, and then what we had was a CR circuit. So here is our capacitor, and here is our resistor. Okay, and we'll put a voltmeter across it. Now remember, this voltmeter is across the capacitor and the resistor. It reads the same voltage, if that makes sense, because it's in parallel with them. There we go. And we're going to ask ourselves the question, what does the voltmeter read? After 40 seconds. Okay, my handwriting never looks good at the best of times, but in black it's absolutely dreadful. Right, okay. Well, you can't answer that question. It's impossible because you haven't got any numbers. Good, let's move on. No, only joking. What we're going to do here is put some values on this, and then we can start to work out what's going on. So we've got C here. We've got R there, we've got V there, which is going to change, and we've got V0 here, V at time t equals 0, and we'll make the voltage here 6.0 volts. Okay, so I've measured to 1 decimal place, 6.0 volts. Okay, for the capacitance, we'll have a typical capacitance of 200 microfarads. Okay, so don't forget the micro there. And for the resistor, I've got sort of, what value did I want to choose? About 150 kiloohms should do the trick. Okay, so that's our R value, and this is our C value. Okay, so we need an equation to solve this. We're going to use the voltage equation. What's the voltage after 40 seconds? We've got V0, we know E, we know T is 40 seconds, and we know the value of C, and we know the value of R. So we work out the right-hand side of the equation. That will give us the left-hand side, and it will give us the voltage on the voltmeter after this has been switched off and the capacitor has been discharging for 40 seconds. So let's see if we can do that calculation, or maybe even better, spacebar, pause the video now. Is it K as well on the keyboard, I think, in YouTube? Pause the video now, work it out for yourself, see what you get, and then I'm going to work through it with you in a minute. Okay, so how did you get on? You know you're right, or pretty right, if the number you got was lower than the supply voltage. If it was higher, well done. Don't know how that's happened. Well, I do know how it's happened. You've forgotten that minus there. So let's have a look at this. We need our equation. So the voltage, when we've left it for 40 seconds, will be equal to the starting voltage reduced by E to the minus T upon CR. Okay, so the voltage that we will calculate is going to be equal to the supply voltage 6.0 all times by E to the power of, now here's where it gets a little bit messy, 40 seconds. Okay, all over CR. Now, this is really important. C 200 times 10 to the minus 6 multiplied by 150 times 10 to the minus 3. Okay, I'll just stick that in brackets, though I don't need to. Now, that's going to give the wrong answer. Exponential decay. So minus that value. And the other thing that goes wrong at A level is you forget the micro and you forget the kilo. Okay. If you bash that out, okay, you find that this slot up here comes out as minus, I think, 1.3 recurring. Okay. Then when you raise E to the power of it, I think you get about 0.26. Okay. So that's smaller. Yeah, 0.26 times that. So V comes out as 6.0 times 0.26, and I get 1.6 volts. All looks good, sounds good, and I think we've retained the right number of significant figures as well. Okay, so I hope you could follow that, and I do hope you got that answer correct, because if you did, it means I did my job properly. Okay, so let's do a practical now. It's going to be a theoretical practical because you're not here, but this is what I'd normally get you to do if you were in class with me. Okay, I would get you to build a capacitor circuit up, like we've just done, a CR circuit, and then what I would do is get you to disconnect the power supply and measure the voltage at different times to see that exponential decay of voltage across the capacitor. So bear with me. To do this, we need to kind of redraw our little circuit because I think it helps to have it in front of us. So there's our charging circuit, and then here's our external CR circuit. There it is. There's the capacitor. And there's the resistor. Now, you might be getting but you might be getting a little bit bored here and going, well, FJ, you know, why are you teaching us this physics so we can literally pass current through a resistor? You know, boring. Well, okay, there's two reasons. Number one, well, three. One, it keeps me in a job, even during lockdown. Secondly, it makes you understand how capacitors behave. But most importantly, this is not a resistor. You know, boring, it's just a resistor. This is the external load. This is some complex electronics that we're interested in, okay? And we can model that, if it's DC at the moment, with just a resistor, okay? Justified myself there, great. There's the voltmeter. Now, I've done that purely to point out that you can connect the voltmeter across the resistor, but that is still the same as connecting across the capacitor. We've charged up, okay? So we've charged up our capacitor. So there we go, charged up. Disconnect, get rid of the blue circuit, okay, get rid of the battery. And the moment you open the switch, start your stopwatch, read the value on the voltmeter, because that will be V0. Now, to be honest with you, most of you would say, well, for heaven's sake, FJ, just leave the switch closed, measure V0, and go. And as soon as you say go, okay, time starts ticking away. And for every, say, 10 seconds, measure the voltage. So in your practical pag books, here we go, you draw yourself a table, and you'd have the time in seconds and the potential difference in volts. I'll just put volts in volts. I suppose that's not brilliant teaching. Potential difference in volts. Okay. And then time t equals 0, 10, 20, 30, 40, etc. And the bit that students around the world don't appreciate, unless they've been working in a particular type of teaching style, the teacher will pick voltages, and particularly capacitances and resistors, that mean that the value of voltage won't drop to 0 in the first hundredth of a second. Okay? It's something that students don't notice. We pick kit that will work. Okay? If this is a 6-volt battery, I don't get you a voltmeter that has got a full-scale deflection of it of 1/1000th of a volt. You know, why would it do that? Okay? But in the real world, you have to pick the components to suit. Okay, get on with it, FJ. Right, so you know that this value will be V0. And then what will happen is, tick, down here, okay, it will get lower and lower. Okay? And finally, if you wait long enough, the graph is asymptotic, but it will, you know, basically read 0 to the resolution of the meter that you're working with. That's really important, okay? That's why you do things like resolution, that once you're down to the last hundredth of a volt, the meters that we have don't measure to a higher resolution than 100th of a volt, so it'll go 0.01 and then it'll go 0, 0.00. Doesn't mean that the voltage is 0, it just means it's lower than we can measure with that device. Okay? And it's good to label all the bits that are important. There's C and there's R, okay? And you would plot a graph, okay? And I'm not going to do it because I've done it already. You would get the exponential decay of voltage. And I would then ask you to do, what's the fractional drop between here and here, between here and here, between here and here, and it will always drop by the same fraction, the same kind of multiplier, okay? So it might go down by 0.2, then multiply by 0.2, then multiply by 0.2, getting lower and lower and lower. Okay? But what I want you to do here is I just want you to calculate, to make life easier, CR. Okay? Because CR is in that equation that we dealt with. So let's see if we can calculate CR. Well, I need to give you some values of the components if we're going to do that. Okay? So let's have an example value of components. Now, you don't know what I'm up to here. I'm up to something, as you probably guess now that I'm up to something. Let's imagine that the capacitor is 100 micro, I'll say that loud, farads, okay? And the resistor is 200 kilo ohms, so we don't miss those multipliers, okay? CR is going to be equal to 20, okay? Now we've got a problem, and it's this problem I wanted to deal with now. What are the units of CR, or RC as I was taught at school. Okay, well, they're pretty obvious. They're farad ohms. Okay, they're farad ohms. Now, that is a really awful unit. It doesn't help me understand anything. What is a farad ohm? I know I can think of names in my class. After I teach you this, a few of you are going to talk in farad ohms for the rest of your life just to annoy people, because the farad ohm is a unit that you are all familiar with and you all use all of the time. No pun intended. So let's see what a farad ohm actually is. Right, I've got a bit of a challenge now. I've got to show you what a farad ohm is. So we're going to do sort of dimensional analysis. Okay, so on this side of the page, I'll do the farad, and on this side, I'll do the ohm. There we go. Okay, so how do we work out what is embedded in the units of the farad? Well, go hunting for an equation. Q equals CV. Okay, and we know that C is measured in farads, so C, is Q over V. Okay, so we've got farads here, and coulombs per volt. Well, that's what a capacitor does, isn't it? How much charge does it store per volt? That is a farad. Okay, so let's work out what sort of units we've got here to make life a little bit easier. Okay, so capacitance, or the farad, is coulombs per volt. So coulombs, so coulombs per volt. Now volt is joules per coulomb. Okay, so joules, but joules beneath, so joules to the minus 1, per coulomb, so we're kind of beneath and beneath again, so that will be coulombs. Okay, what a horrible unit that is. Okay, shall we just sort that out then? Farad is sort of coulombs squared per joule. Well, that doesn't help you at all. Agreed. Give me a chance. Okay, let's do the ohms now. So let's go for V equals IR. Let's see if I can get through this without making a mistake. R is V over I. Okay, so ohms. Ohms are sort of, well, they're sort of joules per coulomb, joules coulombs to the minus 1, okay, per amp, okay, per amp. But an amp is a coulomb per second, okay, so it's per coulombs per second. Okay, so can you see why I've not done coulombs per second? I've done coulombs to the minus 1 seconds because the dividing here. Okay, right, we're almost there. Perhaps you're quicker than I am on this. So let's have a look at what CR is. So CR is farad ohms. Okay, so the farad is coulombs squared joules to the minus 1. The ohm is joules coulombs to the minus 2. My word. Isn't that strange? Really surprises me every time I do this. Okay. Coulomb squared, coulombs to the minus 2. Joules. Joules to the minus 1. Oh my word, look at that. Okay. So a farad ohm, is measured in units of time. And if we do it in the correct SI units, a farad ohm, is in seconds. Okay, so I said some of you, I'm not going to mention a name, but I can think of someone in my group who for the rest of their life will say, Mum, I'll be with you in 120 farad ohms. Just give me a while. Okay, it'll only take a few farad ohms. Yeah, it's really interesting that CR, is something in capacitor circuits that never changes, because in the circuit you've got a capacitance and a resistance. Okay, they never change in the circuit that you've built. So CR is a constant, and that constant will be measured in seconds. So later on, you'll see why that is really, really useful. CR is called the time constant of a capacitor circuit of this kind. Okay, and I'm really pleased that I actually got this right. Yeah, that I've shown you that it must be in units of seconds. So that was successful, showing that CR, the time constant of any capacitor CR network, is measured in seconds. So let's put that to use, okay? And I'm going to do it graphically again. So we found that CR for our last little example was 20 seconds, okay? And that came about, if you remember, because we had 100 microfarads and we had a 200 kilo ohm resistor, okay? And I better put the units in there, farads, okay? And we remember that the farad ohm is that weird thing. It's not, it's a second, okay? How easy. Right, so let's have a look at this graphically. So we're going to say what happens to the voltage on our capacitor as time ticks away. Now, you're probably going to go off and make some coffee now because you say, well, I know this. You've done it already. Yes, I have, but I'm going to do it with some numbers now. Okay, so this is the voltage on the capacitor. I'll just call it the voltage in volts, potential difference in volts correctly. Okay, and this is the time in seconds. Okay, now I'm just going to pick a big number. It makes the graph easier. Imagine we had a high voltage capacitor. They do exist. And we charged the capacitor up to the power supply, which was a 300 volt power supply. Okay, so you know that the starting voltage on the capacitor up here, yeah, is 300 volts. Okay, now I'm going to put a time axis on here. So we'll do 20, 40, and 60. Okay, I could go on further, but that will do. And I need to put this scale on, so that's going to be around 100 volts, and that's going to be around 200 volts. It really helps to have linear scales and to start at 0. Okay, so what is this CR? You really need to listen to me here. Okay. The CR is the bit for the circuit that you've built that never changes because it's a fixed resistor and a fixed capacitor, whether there's a current, voltage, charge or not. CR is always a value, okay? And in the one that we did, it was 20 seconds, okay? So what you notice is that when you do this experiment and you plot your data, after 20 seconds, you find that the voltage on the capacitor is around 100 volts. It's not exactly 100. I'll come back to that. Okay. And then I think you're probably getting it now, that if you wait for another 20 seconds, so you're here, okay, it's about 33 volts or thereabouts. Okay, I'm estimating here. And then if you wait another 20 seconds, it's about 11 volts. So I'm just going to move over here to do our exponential. See what sort of a mess I make of this. So far, so good. Okay. Oh, that'll do. That'll do. Right. So, what do you notice about this curve? Okay. Well, it has a really, really interesting property. Do you remember E? Okay. So, you remember E was 2.72 or thereabouts. Okay. And the crucial thing is here that, having smudged my data, not using a permanent pen here. Okay. The crucial thing is here, CR CR means something. Okay, so listen to me carefully because I find this difficult to explain. Okay, CR, 20 seconds in this case, is the time taken for whatever you're measuring, voltage, to drop to 1/8 of its value. Okay, CR is the time taken for whatever you're measuring to drop to 1/8 of its value. CR, 1/8. Okay. Now I've used a rule of thumb, something that engineers are good at and mathsy people don't do quite so well. The rule of thumb here is, okay, 1/8 is 1/2.72. And I don't know what that is in my head, but I do know that it's almost 1/2.7, 1/3. It's almost a third. So can you see what I've done here to teach you? I've gone, right, 1/8 of 300 is approximately a third. There's my third. If you take the same amount of time, yeah, CR, 20 seconds, it's dropped to about a third. It's dropped to about a third of that. Constant ratio, do you remember? Okay. So every 20 seconds, in this case, that is the value of CR for our experiment. Okay. What you measure drops by, okay, 1/8 of the value. So, and that is approximately, it's 1/2.72, which is approximately a third, yeah, of the value in the time period CR. Okay. This is 1/8, remember. So you can do that on your calculator. But I've done it in my head here, and I've just gone for a third to make life easy. Okay. Now, look at the values here. So we used our rule of thumb. At the start, it was 300 volts. After 20 seconds, it's dropped to 1/8, which is about a third of that, which is about 100 volts. And after another 20 seconds, a third of that, about 33 volts. And after another 20 seconds, a third of that, okay, approximately 11 volts. Right. Now, I've set questions on this, and it really sorts out the engineers from the mathematicians. Okay. I usually say, I draw the circuit, and then I say the voltage on the capacitor is 11 volts. No graph. I just say it's 11 volts. It started off at 300. How long did you wait for? Okay. And the maths people get in a bit of a tangle. But the engineers go, wonder if FJ's up to something here. Let's just check him out. What happens if I wait 20 seconds? Well, I'll drop to 1/8. What happens if I... Oh, I get it. 1, 2, 3. It's 3/8 lives. Yeah, not half lives. 3/8 lives. So he meant approximately, rule of thumb, we waited for 60 seconds. Okay. So now you've got an understanding of what CR means. Yep. It's the time taken. I think I should write this down, shouldn't I? That CR is the time constant. It's the time taken for, well, take your pick. Q, the charge to drop, or the voltage to drop in the capacitor, okay, or the current, okay, to drop to 1/8 of its value, previous value. Yep, I know I've kind of said that before, but I really want to emphasize that point. And remember that this is approximately a third. I think at A level you'll probably do precise calculations, but as an engineer I kind of got to go, yeah, that's what I want. So I use the number, a third in my head. Good. So that's a good look graphically at the time constant for a CR circuit. So finally, let's look at an example, and I'm going to throw into it everything that we know so far. So let's build a little circuit up. So this circuit, we'll assume it's been charged up already. Okay, so just bear with me for a second as I do a little bit of sketching here, and then I'll show you what I'm up to. Okay, so the first thing is, here's where we connected the battery, and it connected across these two capacitors in series. You can see what I'm up to here. Okay, so we charged them up, and then we disconnected the battery. So here's now our power supply. Okay, this will have those two across them in total will have V0. And I'm not going to discharge them yet, so they'll stay lovely and charged, but I will measure their values. So this one is 200 microfarads. And this one is 100 microfarads. So I hope you're thinking already, we've got to do some maths on that. And I hope you're also thinking that the addition of those two will be lower than the lowest. Okay, I had this described to me a while ago as one of these has small plates, one has large plates, and the charge sort of fills up the small plate, and that's it. That's when the current stops travelling, whatever. We don't need to think about that too much in detail just yet. Okay, it's going to discharge through this resistor, but also through this resistor. Okay, two resistors in parallel, yeah? Okay. And we'll give those some values. So we'll make this one 400 kilo ohms, and we'll make this one 400 kilo ohms as well. That's quite A-levelly. It just makes the maths a little bit easy. Okay. So we've got our circuit now. So we need to find out what capacitor discharges through what resistor. What is CR here? Okay, so CR, well, we need the total capacitance. So the total capacitance, I'm not going to do this, because we've done this in a previous video. 1 over the first one plus 1 over the second one, reciprocaled, okay, and I test my answer by it must be lower than the lowest. So 66.7 micro, don't forget that, farads, okay. And the resistors, they're in parallel. So the rule for resistors is 1 over R1 plus 1 over R2 reciprocaled. Okay, but because they're the same value, it's always lower than the lowest. One path for current, another identical path for current, so twice as much current, so half the resistance. Did I do that too quickly? Never mind. It's not what this lesson's about. Okay, R total will be equal to 200 kilo ohms. Okay, so CR, the time constant for this circuit, is equal to 13.3 seconds. Okay, and we need a question now. So what am I going to ask? Well, what's the current after? What is the current after? Okay, 26.6 seconds. So that's my question. One or two of you getting good at this will spot I'm up to something immediately, as I always am, to try and get you to think about this. Now, why not just pause the video now, okay, have a quick go, see if you can solve it, and I'm going to come back in a second and give you the solution. Good. So I hope you all realised that I tried to catch you out there. As teachers always say, and they're lying, I forgot. It's impossible. You can't do it. And you can't do it because I didn't tell you what the battery voltage was that we charged these capacitors up to. Okay? So you need to know, of course, that these were charged up on a battery that was a 20-volt battery. Okay? For the sake of this, I should really say 20.0 volts, as I'm going to make some effort to get the right number of decimal places, or at least significant figures, as it were. Okay, so pause time. I promise you, you now can solve this problem. Right, so how did you get on? Let's see if you got the right answer. Let's do this question together. Okay, so the first thing you notice, and it's typical of the way I teach, is this is 2CR. Okay, so this current I've asked for happens after 2 time constants. Yeah, 2 time constants. So that's going to help us a bit. Okay. Let's have a look at what the current is when we get started. So the starting voltage will be equal to IR. Okay. Now you might think, well, hang on, isn't this something to do with the battery? Yeah, but think about that V0 is on the capacitor. So the current at the start when the capacitor discharges, yeah, that's the capacitor, will be equal to IR. Okay, so we need to work out what I is. So I, the initial current, yeah, will be V0 over R. Okay, so V0 is 20.0 and R is our 200 kilo ohms. Okay, 200 times 10 to the 3. Okay, and therefore the starting current will be equal to 1.00 times 10 to the minus 4 amps. Okay, so we've got the starting current. So all we've got to do is say what is it after 1 time constant, 1/8 of it, and then what is it after 2 time constants, 1/8 of that. Okay, so we're almost there. So let's continue working here. We've got our starting current. Yeah. So after 1 time constant, yeah, it will be 1.00 times 10 to the minus 4 amps. Okay, divided by, so 1/8, I'll write it in sort of old-fashioned terms, yeah. And if you remember, E is 2.72, okay, and that equals 3.68 times 10 to the minus 5 amps, so a smaller number, okay. But we've got to wait for 2 time periods, so we've now got to divide this number, so after by E again. So after 2CR, we've got to do 3.6 times 10 to the minus 5 divided by E again. Okay, and as some of you will notice, of course, there's a quicker way of doing this. You know, you just divide by E squared or whatever. But I'm trying to show you the process, and that comes out as 1.35 times 10 to the minus 5 amps. Okay, so I hope you got that answer. Yeah, it's worth pointing out that 1 or 2 of you might have gone about this in a slightly different way, because you could use the formula I taught you earlier on, that the current now is the current at the start multiplied by E to the minus T upon CR. Okay, and if you use that formula, you know the starting current, or you calculate it. You know the time we've left it for. Yep, and we know CR. So you could use that formula and you get exactly the same answer. So I hope you were successful at working that out via whatever method you chose to use. So I do hope you found that really useful and you've got a good understanding now of the maths of how capacitors discharge. I'll be making another video soon. I think it's the final bit on capacitors, which is how they charge up. And then you should have a really good A-level understanding of capacitor behaviour. Look forward to seeing you next time.